2,800,000,000 miles away, a planet screams. Winds moving 1,200 miles per hour, storms the size of Earth, temperatures dropping to 330 degrees below zero, and we have sent exactly one spacecraft there. Today we go to Neptune. We cover why any human who makes it there stays there forever, the fuel math, the broken bodies, the silence, and the storms that never end. If you enjoy the journey, subscribe. We are just getting started. Prepare yourselves. We begin. Picture the farthest you have ever travelled, maybe a cross-country flight, coast to coast, about 2,800 miles. Now multiply that by 1,000,000. You are still not at Neptune. Neptune sits 2,800,000,000 miles from Earth. That number is almost impossible to feel, so here is a better way to think about it. If you drove a car at highway speed without stopping, day and night, no brakes, no sleep, it would take you more than 5,000 years to get there. Your great-great-great-grandchildren would still be driving. The fastest spacecraft humanity has ever built covered that distance in 12 years. 12 years of flying through empty space at speeds no car, no plane, no rocket carrying humans has ever matched in regular operation. And that spacecraft had no crew, no food supply, no air, no need to slow down, land or come back. It just flew past and kept going. Now imagine a crew inside that ship. 12 years of floating in a metal box, roughly the size of a school bus, watching the stars barely move, watching Earth shrink from a blue dot to an invisible speck somewhere behind you. No window big enough to see anything meaningful, just the hum of machines and the faces of the same 4 or 5 people every single day for over 4,000 days. The distance alone does something to the human mind that no training can fully prepare for. Astronauts on the International Space Station orbit just 250 miles above Earth. Close enough for emergency evacuation. Close enough to resupply. Close enough that the ground is still visible beneath their feet. Neptune is 11 million times farther away than the space station. There is no emergency anything at that range. If something goes wrong, it goes wrong forever. Here is the detail that hits hardest. Even light, the fastest thing in the universe, takes 4 hours and 10 minutes to reach Neptune from Earth. 4 hours and 10 minutes at the speed of light. You could watch 4 full movies in the time it takes a beam of light to cross that gap. A radio signal, which travels at the same speed, takes the same amount of time. If an astronaut at Neptune sends a distress call, Earth receives it 4 hours and 10 minutes later. Earth sends a response. That response arrives another 4 hours and 10 minutes after that. By the time anyone on Earth can react to a crisis at Neptune, 8 hours have already passed. And the distance does one more thing that almost nobody talks about. It changes the emotional weight of the mission completely. Every other human mission in history, from the first orbital flights to the moon landings, kept Earth visible. Psychologists call it the overview effect. Seeing Earth from space actually calms astronauts. It creates a sense of perspective, of connection. At Neptune, Earth vanishes entirely. There is nothing visible behind you except black. No blue marble. No pale dot. Just absence. The crew would have to carry their sense of home entirely inside their own heads for 15 years before they even arrived. And that is just the opening problem. Because getting there is only the smallest part of what makes this mission impossible. The engines that would carry a crew to Neptune carry a secret that engineers have known for decades. A secret that closes the door on any return journey before the ship even leaves the ground. Every rocket ever built by humans runs on the same basic idea. Burn fuel. Push exhaust out the back. Move forward. The faster you burn and the more exhaust you push, the faster you go. Simple in theory. Devastating in practice for a Neptune mission. The best chemical rockets humans have ever designed, the same family of engines that carried astronauts to the moon, top out at a speed that sounds fast until you measure it against the distance to Neptune. At full burn, these engines can push a spacecraft to roughly 36,000 miles per hour. That sounds enormous, and against anything on Earth it is. A bullet travels about 1,800 miles per hour, so these rockets are 20 times faster than a bullet. But space is so large that 36,000 miles per hour becomes almost nothing. To reach Neptune in a reasonable human lifetime, you would need to average speeds far beyond what any chemical engine can produce. Engineers have run the numbers every decade since the space age began. The answer comes back the same way every time. Chemical rockets give you a trip measured in decades, not years. Voyager 2, launched in 1977, used something called a gravity assist. It flew past Jupiter, then Saturn, then Uranus, using each planet's gravity like a slingshot to steal speed. Each flyby added velocity without burning any extra fuel. It was one of the most elegant pieces of orbital mechanics ever designed. And it still took 12 years. A crewed ship cannot replicate that exact path, because the planets only line up that way once every 175 years. The 1970s lineup was a rare gift. Waiting for the next one is not a plan. So engineers look at direct routes. Fly straight to Neptune with enough engine power to reach it faster. The calculations get painful quickly. To cut the travel time down to something a human body might survive, say 5 to 7 years one way, you need to burn enormous amounts of fuel during acceleration. Then you have to burn again to slow down as you approach Neptune, or the ship flies past at thousands of miles per hour and never stops. Each burn eats through propellant at a rate that makes the fuel tanks bigger. Bigger tanks mean more weight. More weight means you need more fuel to accelerate. More fuel makes the tanks bigger again. Engineers call this the tyranny of the rocket equation. Every pound of fuel you need at Neptune has to be launched from Earth, and every pound of fuel launched from Earth needs more fuel underneath it just to lift off. By the time you work backwards from the fuel needed at Neptune to the fuel needed on the launch pad, the numbers reach sizes no rocket in history has come close to lifting. And here is the detail that makes it worse. Everything calculated so far is for the trip there. One direction. A single crossing. The fuel budget for stopping at Neptune, orbiting it, and then firing back toward Earth sits on top of everything already described. That return leg does not get added onto the mission like an extra bag. It gets multiplied into the launch weight from the very first moment. The engineers who study this do not say it is unlikely. They say it is, with any engine humans have built or are close to building, physically impossible. The ship would be too heavy to leave the ground. Which raises a single uncomfortable question. What if you built an engine that plays by completely different rules? Imagine you are packing for a camping trip. You need food, water, a tent, and fuel for the drive. Easy. Now imagine the drive is 30 years long. Every calorie you will eat, every drop you will drink, every spare part for every system in your car, and every drop of gasoline for the entire round trip. All of it has to fit in the trunk before you leave your driveway. You cannot stop. There are no gas stations, no grocery stores, no repair shops. If you forget something, it stays forgotten. That is the supply problem for a Neptune mission, and it is only half the story. The fuel half is where the mission math completely falls apart. To understand why, start with a number. A crewed mission to Neptune and back, using the best chemical propulsion engineers can design today, would need to carry enough fuel to do 4 things. Accelerate away from Earth. Slow down at Neptune. Accelerate back toward Earth. Slow down again when arriving home. Each of those burns requires thousands of pounds of propellant. Stacked together, the total fuel requirement becomes larger than anything ever launched into orbit. The Saturn V rocket, the most powerful launch vehicle humans have ever built, could lift about 300,000 pounds into low Earth orbit. A round-trip Neptune mission using chemical propulsion would require a fuel load that makes the Saturn V look like a model rocket. Scientists have estimated the fuel-to-payload ratio needed for a round trip would exceed the physical capacity of any launch vehicle ever designed or currently on a drawing board. And the math does not get kinder when you try to solve it. Every engineer's instinct is to add more fuel. But adding fuel adds weight. Adding weight means the engine has to work harder. Working harder burns more fuel, which means you need more fuel, which adds more weight. The loop closes on itself with no exit. Physicists call this an exponential cascade. In plain terms, it means every solution makes the problem bigger. The only real escape from this loop is an engine that produces thrust without burning chemical fuel at the same rate. Nuclear thermal engines, which heat hydrogen using a reactor instead of burning it, could theoretically cut fuel consumption dramatically. Ion drives, which push charged particles at very high speeds for very little energy, offer incredible efficiency over long distances, but nuclear thermal engines have never flown a crewed mission. Ion drives produce so little thrust that accelerating a crewed ship to useful speeds would take years of constant burning. Every alternative is either theoretical, too slow, or too dangerous to test on a human crew. Which means any mission planning being done today runs into the same wall. The ship can go. The ship can arrive. The ship cannot carry enough fuel to leave. There is a version of this mission that engineers openly admit is possible. Send the ship one way, land a crew on Neptune's moon and leave them there. Supply drops once a decade if the technology improves. A permanent outpost at the edge of the solar system. That version of the mission has been discussed in research circles, and the idea is stranger and more serious than most people expect. But before you consider living at Neptune forever, you have to understand what the journey itself would do to the human body. Because the fuel problem might kill the mission on paper, the biology problem would kill the crew in space. 6 months on the International Space Station is enough to cause measurable damage to the human body. Bone density drops, muscles shrink. The spine lengthens slightly as vertebrae spread apart without gravity compressing them. Vision changes because fluid in the skull shifts forward and presses on the back of the eyes. Astronauts returning from 6-month missions need weeks of physical therapy just to walk normally again. A one-way trip to Neptune would take 15 years minimum, 2.5 times longer than the entire operational life of most space missions, 30 times longer than the average stay at the space station. The human body did not evolve for space. Every system inside you, from your skeleton to your heart to your blood vessels, developed over millions of years in Earth's gravity. Gravity shapes how your body works at the most basic level. Remove it, and the body begins a slow, systematic process of undoing itself. Bone loss in space happens because bones respond to stress. On Earth, every step you take sends a small shock through your legs and spine. Your bones read that stress as a signal to stay dense and strong. In zero gravity, that signal disappears. Bones start releasing calcium into the bloodstream at a rate of about 1% per month in critical areas like the hip and spine. Astronauts on 6-month missions lose about 2% of bone density in those zones. Over 15 years, the math becomes frightening. Even with the best exercise equipment a spacecraft could carry, studies suggest bone loss cannot be fully stopped, only slowed. By year 5, the crew would have bones fragile enough that a hard landing on any surface could cause fractures. By year 10, some members might already be dealing with irreversible structural damage. The skeletons arriving at Neptune after 15 years would be significantly weaker than the ones that left Earth, and the skeleton is one of the easier problems. The heart adapts to zero gravity by pumping less blood. On Earth, the heart works against gravity to push blood up to the brain and down to the legs. Remove gravity, blood distributes more evenly, and the heart reads this as a sign that it does not need to work as hard. It shrinks. Muscle mass in the heart decreases over long missions. In a 15-year trip, cardiovascular degradation would reach levels that have never been studied, because no human has ever spent 15 years in space. Returning astronauts from 6-month missions already show measurable drops in aerobic capacity. Their hearts pump less efficiently. They tire faster. Some experience irregular heartbeats in the months after landing. Scale those effects by a factor of 30, and the crew arriving at Neptune would be physically closer to elderly patients than to the trained astronauts who left Earth. The body would be broken before the destination was reached. And that is before accounting for what space itself fires at the crew from the outside. Because radiation in deep space does something to the human body that gravity loss cannot touch. Something that strikes at the very code your cells use to stay alive. Something that no amount of exercise or calcium supplements can fix. At 6 months in space, bone loss is manageable. Astronauts exercise 2 hours every day on the space station, running on treadmills with harnesses that push them down into the machine to simulate weight-bearing stress. The equipment works well enough to slow the damage. Density drops, but crew members return to Earth and recover within months. At 15 years, exercise alone cannot hold the line. Here is the specific problem. Bone is a living tissue. It constantly breaks down old material and builds new material in a process called remodeling. On Earth, gravity keeps this cycle balanced. In space, the breakdown side of the cycle accelerates while the rebuilding side slows down. The result is bone that gets thinner, weaker, and more porous over time. The hip is one of the most vulnerable areas. Weight-bearing bones in the legs and pelvis depend heavily on the mechanical stress of walking to stay dense. Studies from long-duration space missions show hip bone density dropping at rates that, if continued beyond 2 years without significant countermeasures, would lead to bones comparable to severe osteoporosis cases seen in people in their 80s. Exercise machines on board a spacecraft can apply some of that mechanical stress. Resistance training, vibration plates, and specially designed treadmills all help. Engineers designing the space station included 2 hours of mandatory daily exercise specifically because bone loss data from earlier missions was alarming. But exercise has limits. After roughly 18 months, studies suggest the benefits of exercise in space plateau. The body adjusts to the exercise itself, and bone loss continues at a reduced but steady rate regardless. Over 15 years, the cumulative damage would be severe. Crew members might lose 20 to 30% of bone density in critical areas. Fractures from routine activity become a real risk. The spine, compressed differently without gravity, develops structural changes that are painful and sometimes permanent. Vertebrae shift. Discs bulge. Some astronauts return from long missions with spinal problems that persist for years after landing. And here is a detail that makes the bone situation uniquely cruel for a Neptune mission. Even if the crew could somehow survive the trip and arrive at Neptune, they would be too physically fragile to perform the work the mission required. Setting up equipment, operating mechanical systems, moving in a bulky spacesuit, these all require physical strength and skeletal integrity that 15 years of zero gravity would have stripped away. The crew would arrive broken, unable to do what they came to do, and with no way to get back. Engineers have discussed one potential solution: artificial gravity. If you spin a section of the spacecraft fast enough, the centrifugal force mimics the effect of gravity and gives bones the mechanical stress they need to stay healthy. The concept works in theory and has been studied for decades. Building a rotating habitat large enough to be effective without adding so much mass that the fuel equation becomes impossible has kept this idea on drawing boards for 50 years. No crewed spacecraft with artificial gravity has ever been built, which means the bone problem remains open. And the bone problem is visible, measurable, and at least something doctors can track. What radiation does to the crew is quieter, slower, and far more dangerous. The heart is a muscle. Like any muscle, it grows stronger when it works hard and shrinks when work disappears. On Earth, the heart pumps about 5 litres of blood per minute at rest, pushing fluid up through the body against gravity, making sure the brain gets oxygen and the legs get circulation. It works constantly against a force pulling everything downward. Remove gravity, and that effort changes overnight. In zero gravity, blood does not pool in the legs the way it does on Earth. Without the downward pull, fluid distributes more evenly throughout the body. The heart detects this shift. It reads the even distribution as a sign that the body has more blood volume than it actually needs. In response, the kidneys flush extra fluid. The total blood volume in the body drops. And the heart, no longer fighting gravity to push blood to the extremities, begins to do less work. Less work means less strain. Less strain means the muscle does not need to stay as large. The heart shrinks. Cardiac muscle loss in long-duration space missions has been documented across multiple studies. Astronauts returning from 6-month stays on the space station show measurable reductions in heart mass and pumping efficiency. For most, this reverses after a few months back on Earth, where gravity demands the heart work hard again. But the reversal takes time, and the data on missions beyond 12 months is limited because no human has been in space continuously that long. A 15-year journey to Neptune would shrink the heart in ways that reverse only with gravity. And a Neptune mission provides no gravity for the entire transit. The crew would be living with a progressively weaker heart from year 1 through year 15, with the heart getting worse each year and no recovery possible until they return to gravity. Except returning to gravity is exactly what the mission makes impossible. The cardiovascular effects extend beyond the heart itself. Blood vessels adapt to zero gravity by losing some of their elasticity. Without the constant pressure of gravity-driven blood flow, vessel walls do not need to be as responsive. They stiffen slightly over time. This is connected to why some astronauts experience elevated pressure inside the skull. Stiffer vessels, redistributed fluid, and the absence of the gravity gradient that normally keeps fluid moving downward all combine to push cerebrospinal fluid toward the head. This pressure increase causes visual changes in a significant number of astronauts. The back of the eye, the structure called the optic nerve head, gets pushed outward. In some cases, eyeball shape changes enough to cause permanent vision impairment. Roughly 40% of long-duration astronauts on the space station report some level of vision deterioration. Over 15 years, the progression of that damage enters completely unknown territory. The crew heading to Neptune would be doing so with shrinking hearts, stiffening vessels, and eyes slowly deforming inside their skulls, all before a single threat from the environment outside the ship touched them. And outside the ship, one threat above all others was waiting with infinite patience. A threat that works at the level of individual cells. A threat that doctors cannot treat, cannot reverse, and cannot fully protect against. Something that turns the body's own instruction manual against itself. Open space is full of things you cannot see. One of the most dangerous is cosmic radiation. On Earth, you are protected by 2 layers of defense. First, the planet's magnetic field deflects the most energetic particles coming from deep space. It acts like a force field around the entire planet. Second, the atmosphere absorbs what gets through, filtering out the most harmful wavelengths before they reach the ground. Together, these 2 layers reduce your radiation exposure to almost nothing on a daily basis. Step outside those layers, and everything changes. In deep space, between Earth and Neptune, there is no magnetic field shielding the ship. There is no atmosphere. Cosmic rays, which are high-energy particles travelling at nearly the speed of light, fly through the ship constantly. They pass through metal walls as easily as a rifle round through paper. They pass through the human body at the same rate. When a cosmic ray hits a cell in the body, it can break the DNA inside that cell. DNA is the instruction manual for everything the cell does: how to divide, how to function, when to stop growing. A break in DNA is not always fatal to the cell. The body has repair systems that fix most breaks quickly. But cosmic rays do not hit one at a time. They hit continuously from all directions around the clock. Over months, the repair systems start to fall behind. Over years, damaged DNA accumulates. Cells with broken instructions start behaving abnormally. Some die. Some multiply out of control. The clinical name for cells multiplying out of control is cancer. Scientists studying radiation exposure in space use a unit called a sievert to measure the biological dose of radiation the body absorbs. The yearly dose from natural background radiation on Earth is about 1,000th of a sievert. The yearly dose aboard the International Space Station, which is still inside Earth's magnetic field, is roughly 1/10th of a sievert. The yearly dose in deep space outside Earth's magnetic field is estimated at about 1 sievert per year, or higher depending on solar activity. 1 sievert per year. For 15 years. Before reaching Neptune. Cancer risk grows with each sievert accumulated. Studies on atomic bomb survivors and radiation accident victims have allowed scientists to map out what different exposure levels do to long-term health. The dose a Neptune crew would accumulate on the outbound trip alone would exceed the lifetime career limits set by space agencies for astronauts who spend their entire careers in low orbit. And beyond cancer, radiation attacks the brain. High-energy particles passing through brain tissue can damage neurons directly. Studies on mice exposed to the type of radiation found in deep space showed measurable cognitive decline, including memory loss, reduced problem-solving ability, and increased anxiety behaviors. Whether the same effects translate to humans at the same scale is still being studied, but the evidence points in one direction. You would arrive at Neptune having accumulated a radiation dose large enough to cause serious long-term damage, and you would have no way to fix it. Engineers know all of this, and their answer to radiation has its own devastating cost. The straightforward answer to radiation is shielding. Surround the crew compartment with material thick enough to stop cosmic rays, and the crew survives the journey. The logic is clean, the physics is brutal. Stopping cosmic radiation requires mass, lots of it. Water is actually one of the better shielding materials available, more effective per pound than steel for certain types of radiation, because hydrogen atoms in water are good at absorbing high-energy particles. Polyethylene plastic is another option. Lead works for some radiation types, but is extremely heavy and less effective against the specific particles found in deep space. The problem is the amount of material required to provide meaningful protection over 15 years of exposure. A shielding layer thick enough to cut the radiation dose significantly would add hundreds of thousands of pounds to the spacecraft. Some engineering proposals suggest a water wall around the crew habitat, essentially building the ship inside a shell of liquid, to provide radiation protection while also serving as part of the water supply. Even optimistic versions of this design add staggering amounts of mass to the mission, and mass is the one thing the mission cannot afford. Every pound added to the spacecraft requires more fuel to accelerate. More fuel means more weight at launch. More weight means even more fuel underneath it to get off the ground. The cascade from the rocket equation, already crippling for a Neptune mission, gets worse with every pound of shielding added to protect the crew. Engineers call this a mass penalty. Adding protective shielding makes the radiation problem better and the fuel problem worse at exactly the same rate. Every solution creates a new version of the same constraint. The practical result is that mission designers are forced to choose between two bad options: build a ship light enough to actually launch, and the crew arrives at Neptune having absorbed a lifetime of radiation damage, or build a ship heavy enough to protect the crew, and the ship never leaves the ground at all. Neither option delivers a crew to Neptune and back alive. Some researchers propose solving this by using the supplies themselves as shielding. Pack food, water, and equipment around the crew compartment in layers designed to absorb radiation. As the mission progresses and supplies are consumed, the shielding thins, which means the crew faces more radiation in the later years of the trip, precisely when their bodies are already weakened from years of space travel. The shield gets thinner as the journey gets longer. The crew gets more fragile as the radiation increases. The two curves cross at exactly the wrong time. There is one technology that could change this calculation entirely, an engine so efficient it could carry both the crew and the shielding without breaking the fuel equation. Engineers have been designing it on paper for decades. Governments have funded early research on it multiple times, and every time the same obstacle appears. What happens inside that engine would make most people deeply uncomfortable. Imagine something goes wrong on the ship. An oxygen line cracks in year 8, a navigation computer fails, a crew member shows symptoms of an unknown illness. The crew sends a message to Earth describing the problem and asking for help. 4 hours and 10 minutes later, that message arrives at Earth. Engineers and doctors on the ground scramble. They calculate solutions, write instructions, record a response. They send it back. 4 hours and 10 minutes later, their response arrives at the ship. More than 8 hours have passed since the crew first reported the crisis. In a medical emergency, in a technical failure, in any situation where seconds or minutes matter. 8 hours is not a delay. 8 hours is a death sentence. This communication gap is the direct result of distance. Radio signals travel at the speed of light, and even at the speed of light, crossing 2,800,000,000 miles takes 4 hours and 10 minutes. There is no technology that makes this faster. Nothing in physics suggests anything ever will. The gap is not an engineering problem. It is a law of the universe. Astronauts on the Moon were 1.5 seconds away from Earth by radio, a delay noticeable in conversation but manageable in a crisis. Mars, depending on where it sits in its orbit, creates communication delays between 3 and 22 minutes. Long enough to be frustrating. Short enough that a slow-moving emergency can still get guidance from Earth before the situation becomes catastrophic. Neptune's 8-hour wall changes the mission at its most basic level. A crew at Neptune is not an outpost with support. It is an island. Completely self-contained. Completely alone. Every decision the crew needs to make, every repair, every medical treatment, every navigation calculation, they handle it themselves. Earth cannot intervene in time to matter. Mission control becomes a historical record rather than an active partner. Ground teams can send information, updates, encouragement, but they cannot help. This level of isolation has never been tested on a human crew. Astronauts on the space station are only about 1 second away from Earth by radio, and psychological support from the ground is considered a critical component of crew mental health during long missions. Station crews know that if something goes catastrophic, an emergency vehicle can reach them within hours. That knowledge matters. It changes how the mind handles stress. A Neptune crew would have no emergency vehicle, no rapid response, no real-time guidance. The ground team would be watching a version of events that was 4 hours old at minimum. By the time Earth knew the crew was in trouble, the crew had already been dealing with it alone for 4 hours. Training can compensate for some of this. Crews can be prepared with procedures for every foreseeable emergency. Artificial intelligence systems could assist with real-time problem-solving on board. But no preparation eliminates the fundamental fact that at Neptune, the crew is entirely on its own. And that fact does something specific to the human mind over months and years of isolation. Something that no amount of professional training fully prevents. Something that has shown up, in smaller forms, in every long-duration mission ever flown. In the 1960s, a Soviet researcher named Valery Ryumin wrote something in his mission diary that became famous in space medicine circles. He wrote that all the conditions necessary for murder are met by placing 2 men in a small cabin for 2 months. Ryumin was joking. Mostly, the psychology of isolation is one of the least discussed and most serious challenges in long-duration spaceflight. Researchers have studied it through Antarctic winter over missions, submarine deployments, isolated habitat simulations, and the growing data from long-duration space station stays. The findings are consistent enough to be alarming when projected onto a 15-year Neptune transit. In the early months of isolation, most people adapt well. There is novelty, there is purpose, there are tasks to perform and discoveries to make. Crew members who train together for years build strong bonds that sustain them through initial difficulties. Around month 6 to month 12, something shifts. The novelty fades, the routine becomes oppressive. Small irritations that were easy to brush off at the start grow into sources of real friction. Researchers studying Antarctic crews in winter-over conditions found that interpersonal conflicts, depression, and cognitive slowdowns all peaked in the middle phase of a long isolation, long after the initial excitement and well before any light at the end of the tunnel. A Neptune mission would enter that middle phase somewhere around year 1 and stay there for another 13 years. Psychologists who study this call it the third quarter phenomenon. In almost every long isolation study, the emotional low point hits around 3/4 of the way through the mission. For a 15-year transit, 3/4 of the way is year 11. The crew would be closest to their lowest psychological point at the exact moment they approached Neptune, the moment requiring the most focus, the most technical precision, and the most coordinated teamwork. The behavioural countermeasures available are limited. Private communication with family on Earth, delayed by 4 hours each direction but still valuable. Structured schedules to provide routine and purpose. Conflict resolution protocols. Onboard entertainment and virtual environments. Psychological support from Earth-based teams sending recorded sessions. These tools help. They do not solve the problem. Studies from Antarctic stations and submarine crews show that even motivated, well-trained professionals experience measurable personality changes during extreme long-term isolation. Decision-making slows. Risk tolerance shifts. People who were cooperative at the start of a mission develop fixed conflicts that no mediation resolves. And if one crew member crosses a line, physically, psychologically, or in terms of mission safety, there is no way to remove them. No emergency return. No replacement. The crew lives with whoever is on the ship for the full duration. The human mind was shaped by a world of open spaces, social contact, sensory variety, and the ability to leave. A Neptune transit removes every one of those things. And that removal does not stay quiet. The psychological damage accumulates alongside the physical damage. Both are invisible at first. Both become impossible to ignore over time. And both would reach their worst point at exactly the same moment, just as the crew arrived at their destination. What waits at Neptune is strange enough to make the journey seem calm by comparison. Stand outside during a Category 5 hurricane. The wind is moving at 150 to 180 miles per hour. It is strong enough to peel the roof off a building, carry cars sideways, and turn loose debris into projectiles. A Category 5 is the most violent storm a human can experience on Earth, and most structures are not built to survive one at full strength. Neptune's winds move at 1,200 miles per hour. That is not a misprint. 1,200 miles per hour. More than 6 times faster than the strongest hurricane ever recorded on Earth. Fast enough that the wind itself would move at nearly double the speed of sound in Earth's atmosphere. Fast enough to strip the surface off anything exposed to it within seconds. And these winds are constant. Hurricanes on Earth last days, sometimes weeks. They dissipate because they draw energy from warm ocean water, and they eventually run out of warm water to feed them. Neptune has no warm ocean surface. It receives almost no heat from its star because it sits so far away that high noon on Neptune looks like deep twilight on Earth. Despite that, the winds keep blowing at speeds that break every comparison available. Scientists are still working to understand how Neptune generates winds that violent with so little incoming energy. The best current explanation involves heat escaping from deep inside the planet, leftover warmth from Neptune's formation billions of years ago. The interior of Neptune is actually warmer than the surface temperature of some planets closer to the star. That internal heat drives atmospheric circulation, creating the enormous wind patterns that have persisted for as long as humans have been able to observe them. For a crew arriving at Neptune, these winds create an immediate, practical problem. Getting to Neptune means slowing the spacecraft down enough to enter orbit. Any attempt to descend into the atmosphere would mean flying through winds moving at 1,200 miles per hour in a vehicle never designed to handle that kind of aerodynamic force. The structural stresses would be extraordinary. Engineering a spacecraft to survive atmospheric entry into Neptune's wind layer would require materials and design tolerances far beyond anything currently used in space exploration. The Voyager 2 flyby in 1989 gave humanity its first close look at Neptune's wind systems. The probe detected wind speeds as it swept past, and the data stunned researchers. The winds at Neptune move in the opposite direction to the planet's rotation in some bands, a phenomenon also seen on Venus but at nowhere near these speeds. Scientists still debate the exact mechanisms responsible. From orbit, a crew could observe those winds from relative safety. The planet below would be a churning blue sphere wrapped in streaks of white cloud moving at incomprehensible speed, beautiful, terrifying, and completely impenetrable. And orbit itself comes with a challenge nobody thinks about until the engineers start calculating. Getting into orbit around Neptune requires fighting the planet's gravity. Neptune's gravitational pull is 17 times stronger than Earth's. Matching that gravity with engine burns takes fuel. And fuel, as established, is the one thing the mission can least afford. But the winds and the gravity are almost calm compared to what happens below the cloud tops. Every mission to another world in human history has imagined a crew eventually landing, setting foot on a surface, collecting samples, planting flags, the moon landings, the Mars missions being planned, the proposals for Europa or Titan. All of them involve a solid surface somewhere at the destination. Neptune has none. Neptune is an ice giant, a category of planet that sits between the gas giants like Jupiter and the rocky worlds like Earth. The atmosphere starts as a thin layer of hydrogen and helium gas at the top and gradually thickens as you descend. There is no moment where you transition from sky to ground. Instead, the gas gets denser, temperature rises, and pressure increases without any boundary marking where the atmosphere ends. Descend far enough, and the gas blends into something that behaves more like a fluid than a gas. Pressures that would crush a nuclear submarine in seconds, temperatures rising to thousands of degrees despite the freezing cold at the cloud tops. The chemistry changes as the depth increases, with hydrogen and helium giving way to water, ammonia and methane in strange high-pressure states that do not exist anywhere on Earth. Go deeper still, and you reach what scientists describe as a mantle of superionic water. Water in a state where the oxygen atoms lock into a crystalline structure, while the hydrogen atoms flow freely like a liquid. Nothing in everyday experience resembles this. It is a state of matter that only exists under pressures so extreme that the atomic structure of the material changes. Below that, somewhere near the centre of Neptune, a rocky core sits buried under thousands of miles of crushed ice and impossibly pressurized fluid. The core itself is estimated to be roughly the mass of Earth, sitting at temperatures in the thousands of degrees, kept hot by the immense pressure compressing it from every direction. A crew arriving at Neptune has nowhere to land. They cannot descend to collect fuel or resources from the planet. They cannot set up a surface base. They orbit. They observe from a distance. They cannot reach the interior where all the scientifically interesting states of matter exist without being crushed long before getting there. This has a specific consequence for the mission's survival. One of the theoretical strategies for making a crewed Neptune mission more feasible involved using resources at the destination to help fuel the return journey. Scientists have proposed this for Mars missions as well, where crews could extract water from the Martian soil and convert it into rocket propellant on site. The concept is called in situ resource utilization, and it has become a cornerstone of long-range mission planning. At Neptune, there is no surface to extract anything from. The resources are there in abundance: hydrogen, methane, water, deep below the cloud tops. But reaching them is beyond any technology available or near-term foreseeable. The crew arrives at a planet filled with fuel and cannot access any of it, which leaves them entirely dependent on whatever they carried from Earth, and carrying enough of everything for decades in space is a problem that makes the fuel equation look simple. Neptune's colour is one of the most striking things about it. In photographs taken by Voyager 2 and refined by telescope observations since, Neptune appears as an intense, vivid blue, deeper and richer than any ocean colour, almost artificial looking, like someone painted it. The colour comes from methane gas in the upper atmosphere. Methane absorbs red light and reflects blue light back into space. The effect is so strong that Neptune's blue is noticeably deeper than Uranus, which also contains methane, but in different concentrations. Scientists are still working out exactly why Neptune's methane produces such a saturated blue, while Uranus, with a similar composition, appears a paler blue-green. Something else is in Neptune's atmosphere that has not been fully identified yet. That unknown component is a small example of a larger truth about Neptune. Despite being the 8th planet in our solar system, and despite Voyager 2's flyby in 1989, Neptune remains one of the least understood planets in our neighbourhood. The flyby gave humanity 36 hours of close observation, 36 hours across 8.5 billion years of the planet's existence. Scientists are working from the equivalent of a single paragraph in a book with no other chapters. For a crew descending into that atmosphere, the visuals would be extraordinary and the danger would be immediate. The upper cloud layers consist of methane ice crystals at temperatures of around -330 degrees Fahrenheit, far colder than any temperature ever recorded on Earth's surface. Cold enough to freeze carbon dioxide solid, cold enough that unprotected human skin would sustain frostbite in seconds and begin freezing within minutes. At those temperatures, most metals become brittle. Rubber seals crack. Lubricants used in mechanical joints solidify. Any component of a spacecraft designed to flex, seal, or move would need to be built from specialized materials tested for extreme cold. Standard spacecraft components are not designed for Neptune's upper atmosphere temperatures. Even the materials used on missions to other cold environments like Mars or Europa require modification for Neptune conditions. Descending further, the temperature paradoxically rises as pressure builds. But the rising temperature does not bring relief. Instead, it brings a new kind of danger. The combination of extreme pressure and chemically active compounds in the deep atmosphere would attack the materials of any probe or vehicle attempting to go lower. The Galileo probe, which descended into Jupiter's atmosphere in 1995, survived for about 57 minutes before pressure and temperature destroyed it. Neptune's atmosphere, while different in composition, presents similar destruction timelines for any object attempting deep entry. A crew in orbit would watch the blue surface from thousands of miles above, knowing that the atmosphere below them was cold enough to freeze metal at the top and hot enough to melt it deeper down. With a wall of 1,200 mph wind between them and any closer look. And somewhere even stranger waits below the deepest layer any probe has ever reached. Beneath the wind, beneath the methane clouds, beneath the layers where temperature and pressure have already exceeded anything survivable, Neptune holds something that has no direct comparison anywhere on Earth. A super-hot ocean. Scientists call it a water ammonia mantle, but those words do not capture what it actually is. Picture an ocean thousands of miles deep, sitting at temperatures between thousands of degrees and tens of thousands of degrees, under pressure so extreme that the water itself cannot behave like water anymore. On Earth, water has 3 states: solid ice, liquid water, and water vapor. These states exist because of temperature and pressure. At standard conditions, water freezes at 32 degrees Fahrenheit and boils at 212. Increase pressure enough and the boiling point rises. In an industrial pressure cooker, water stays liquid at temperatures that would flash boil it at sea level. Go to the pressures inside Neptune, and water reaches states that have no everyday name. The oxygen and hydrogen atoms that make up water get separated by the crushing pressure and temperature. The oxygen atoms lock into a crystal-like structure. The hydrogen atoms, stripped to their cores, flow freely through the gaps in that crystal like a current of liquid metal. Scientists call this superionic water, it conducts electricity. It is simultaneously solid and liquid depending on which atoms you are watching. This material does not exist anywhere on Earth's surface. Researchers have created tiny amounts of it in laboratories using diamond anvil presses that generate pressure by squeezing a sample between two diamonds. The experiments last fractions of a second and produce quantities too small to see without a microscope. Everything known about supersonic water comes from those brief, extreme experiments and from the mathematical models built around them. Inside Neptune, this state of water extends for thousands of miles, and the electrical currents flowing through it are likely what generates Neptune's magnetic field, a field that is tilted 60 degrees away from the planet's rotation axis. On Earth, the magnetic poles are close to the geographic poles. On Neptune, the magnetic field emerges from a point far off centre and tilted sharply, which scientists believe is a direct result of the strange conducting properties of the supersonic water layer beneath the clouds. A crew orbiting Neptune could measure this magnetic field from a safe distance. They could analyse its strange tilt. They could model the deep ocean through its effects on the planet's radiation environment and electromagnetic signatures. Getting any closer than orbit is not possible without being crushed and dissolved before reaching anything worth studying. The planet holds an ocean that humans can detect, partially model, and never visit. An ocean where water behaves like no water on Earth, conducting electricity through a crystal of oxygen while hydrogen flows through it like a ghost. Below even that ocean, buried under everything, something else waits. A core older than Earth's recorded history, sitting at temperatures a blowtorch could not reach, locked in a prison of pressure that no human technology will crack for generations. And above all of it, the storms rage on. Stand outside on a clear day at noon. The light is bright enough to make you squint, bright enough that looking directly at the source would damage your eyes in seconds. That noon brightness on Earth comes from a star 93 million miles away. Neptune is 2,800,000,000 miles from that same star, 30 times farther from it than Earth. At that distance, the light arriving at Neptune is 900 times dimmer than what reaches Earth at noon. 900 times dimmer. High noon on Neptune looks like deep twilight on Earth. The kind of light you get about 20 minutes after sunset when the sky still holds a faint glow but nothing casts a shadow. Dim enough that you would struggle to read a book. Dim enough that plants on Earth placed under Neptune's noon sunlight would not be able to photosynthesize. Dim enough that a human standing on a surface there, if such a surface existed, would have difficulty distinguishing colours clearly. And this is at noon. The brightest moment of Neptune's day. Neptune's day is only about 16 hours long. It rotates faster than Earth despite being 58 times larger in volume. But its year is staggering. Neptune takes 165 Earth years to complete one orbit around its star. 165 years. When astronomers first spotted Neptune through a telescope in 1846, it was beginning a journey around the star that would not be completed until 2011. Every person alive at the discovery was dead by the time the planet finished its first observed orbit. For a crew at Neptune, daylight and darkness would alternate on a 16-hour cycle, but neither would feel like day or night as humans know them. The dim noon would feel like early evening. The darkness would be total, with only the stars and the faint glow of Neptune's star. Now just a very bright star rather than a blazing disk, providing any light at all. The star itself, from Neptune, loses its disk shape to the naked eye. It becomes a point of intense light, the brightest star in the Neptune sky by a massive margin, but still just a point. Planets in our solar system would be visible from Neptune, but most would require binoculars to see clearly. Earth, from Neptune's distance, would be invisible to the unaided eye. A crew at Neptune would experience a sky where the familiar star is just another bright point, where Earth cannot be found, and where the dim light of high noon provides less illumination than a cloudy afternoon anywhere on Earth. The experience of being that far from everything familiar is an aspect of a Neptune mission that cannot be simulated in training. The psychological weight of that darkness, that distance, that dimness, would settle on the crew from the moment they arrived, and at Neptune the dark does not sit still. In 1989, Voyager 2 flew past Neptune and photographed a storm so large it covered an area equal to the entire surface of Earth. Scientists called it the Great Dark Spot. It sat in Neptune's southern hemisphere, a massive oval of swirling cloud rotating counterclockwise, surrounded by white methane ice clouds forming and dissolving along its edges. The dark centre measured roughly 7,000 miles across. Compared to it, the largest hurricanes on Earth look like puddles. Winds at the edges of the Great Dark Spot moved at 900 miles per hour as measured by Voyager 2. Even the boundaries of the storm moved at speeds Earth's most violent weather could not touch. Then, in 1994, the Hubble Space Telescope turned toward Neptune for a follow-up observation. The Great Dark Spot was gone. In 5 years, the largest storm anyone had ever observed in the solar system had completely disappeared. A storm the size of Earth, sustained for at least the duration of Voyager 2's approach and flyby observations, had simply ceased to exist. By 2018, a new dark spot had formed in Neptune's northern hemisphere. Scientists watching it noted it was drifting toward the equator, a behaviour that had never been observed on Neptune. On Earth, hurricanes moving toward the equator weaken and dissipate. In 2022, instead of dissipating, Neptune's northern dark spot spawned a smaller companion storm that detached and disappeared independently, while the main storm survived longer than any storm model predicted. What drives these storms is still not fully understood. The storms on Jupiter, including the Great Red Spot which has persisted for centuries, are powered by heat from below and the planet's rapid rotation. Neptune's storms appear and vanish on timescales of years, which suggests a different mechanism. Scientists believe Neptune's internal heat drives weather patterns differently than Jupiter's, creating storms that can build to planet-scale size and then collapse entirely when some internal threshold shifts. For a crew orbiting Neptune, watching this weather system from above would be one of the most visually extraordinary experiences any human had ever had. A storm the size of their home planet, churning below them, surrounded by streaks of white cloud moving at speeds that would level any city on Earth. And they could not get closer. The winds beneath the cloud deck would destroy any probe before it could return useful data, let alone any crewed vehicle. The crew would orbit above an alien weather system that defies prediction, generated by mechanisms still partially unknown, capable of disappearing entirely in 5 years or surviving longer than any model expects. And somewhere in the orbit of Neptune, a moon circles backwards, slowly falling, scheduled for destruction in the most distant future imaginable. Its story reveals something violent about Neptune's past that nobody expected. Before any crew leaves Earth for Neptune, someone has to answer a single question. What do you pack for a 30-year round trip to a place with no stores, no resupply ships, no repair services, and no way to get help? The answer is everything. And the weight of everything is what breaks the mission before it starts. A human being at rest burns roughly 2,000 calories per day. Active astronauts doing physical work and daily exercise routines can burn closer to 3,000. For a crew of 4 people on a 15-year one-way trip, the food alone works out to roughly 65 million calories before the first day at Neptune. Every bit of it has to leave Earth in sealed packaging that survives years of temperature swings, radiation exposure, and mechanical vibration. Water is partly solvable through recycling. The space station already recycles around 93% of its water, including sweat and urine, back into drinkable water. A Neptune mission would need a recycling system that performs at that level for 15 years without a single critical failure. Any drop below 90% efficiency, sustained for months, begins to create a shortfall that cannot be made up. spare parts are the hardest problem. Every mechanical component on the ship has a lifespan. Pumps wear out, filters clog, seals degrade. Electronics fail. On the space station, a replacement part can be launched from Earth and arrive within days. On a Neptune mission, there are no replacement parts after launch day. Every part that might ever be needed for 30 years has to be packed before departure. Engineers call this the long tail problem. Most failures are predictable, and the parts for them are easy to include. But spacecraft are complex enough that rare, unexpected failures happen. The parts for those failures are hard to predict and harder to pre-pack. Over 30 years, the number of unexpected failures approaches certainty. At some point, something will fail that the crew has no spare for. On the space station, that scenario leads to an emergency resupply mission. On a Neptune transit, it leads to a decision about whether the mission continues. The mass of everything required adds up fast. Food, water reserves, spare parts, medical supplies, exercise equipment, scientific instruments, emergency systems, replacement components for life support, fuel for maneuvering in Neptune's orbit. Packing 30 years of complete self-sufficiency for a crew of 4 adds hundreds of thousands of pounds to the mission before the propulsion system is even considered. Every pound added requires more fuel to accelerate. More fuel adds more weight. The mass cascade from the rocket equation keeps running. Engineers who have tried to design a complete mission manifest for a crewed Neptune return have found that the numbers grow faster than the technology to lift them. The crew would have to leave knowing that some part of their ship would eventually fail without a replacement, that some system keeping them alive had a clock running down somewhere that they could not see. And the clock on one system in particular, one that no backup can fully replace, had already started running the moment the ship left orbit. Every machine ever built by humans starts degrading the moment it begins operating. Rubber seals compress and crack. Metal parts develop microscopic fractures from repeated stress cycles. Lubricants slowly break down. Electronics accumulate damage from heat cycles, vibration, and radiation. On Earth, we manage this through maintenance, replacement, and regular inspection by trained technicians with access to workshops and parts. In space, none of those resources exist. The space station has survived for over 2 decades through a continuous flow of replacement components, visiting crews carrying spare hardware, and astronauts performing spacewalks to swap out failing equipment. The station has had water recycling failures, toilet system breakdowns, oxygen generation malfunctions, and power system issues. Every single time, Earth sent a fix, a new part, a new crew member with specific skills, a replacement unit launched on the next cargo ship. A Neptune mission gets none of that. Whatever condition the ship is in on departure day is the best it will ever be. From that moment forward, every system moves in one direction, toward failure. Engineers design spacecraft with redundancy to manage this. Redundancy means building 2 of everything critical, sometimes 3. If one oxygen generator fails, a backup takes over. If one computer crashes, a second computer runs the same calculations simultaneously. If one thruster misfires, a parallel set of thrusters compensates. Redundancy buys time. It does not prevent failure. It means the first failure is survivable. The second failure of the same system is often not. Over 15 years, redundant systems begin failing one at a time. A backup oxygen generator that was never meant to run continuously becomes the primary unit after its twin fails in year 4. It was designed to operate for 2,000 hours as an emergency backup. By year 8, it has been running for 35,000 hours. The stress on components was never anticipated in the original design. Voyager 2 provides the clearest real-world example of long-duration spacecraft degradation. Launched in 1977, the probe has now been operating for nearly 50 years. Over that time, engineers have had to repeatedly adjust power management as the probe's nuclear battery slowly loses output. several science instruments have failed permanently. The probe's ability to transmit data has dropped as its power supply weakens. Voyager 2 is still operating, but with a fraction of its original capability. Voyager 2 carries no crew. It does not need to maintain air pressure, water recycling, temperature control, or food storage. It does not need to fire maneuvering thrusters with precision. The systems a crewed ship requires are vastly more complex than those of a scientific probe, and they must perform far more precisely for far longer. A critical failure in a life support component in Year 12 leaves the crew with limited options. Repair it with whatever materials and skills are available on board, hope the repair holds, and continue. Or face consequences that cannot be patched with tape and ingenuity. The ship that reaches Neptune after 15 years would carry the accumulated damage of a decade and a half of deep space exposure. Radiation hardened but not radiation immune. Mechanically stressed. Running on systems that had survived far longer than their rated lifespans. And returning home would require every one of those systems to keep functioning for 15 more years. The history of the only spacecraft to ever reach Neptune tells part of that story. But what Voyager 2 actually saw when it arrived reveals something even the engineers did not fully expect. On August 25, 1989, a spacecraft the size of a school bus flew past Neptune at 36,000 miles per hour and changed everything scientists thought they knew about the outer solar system. Voyager 2 had been travelling for 12 years. Launched in 1977 from Cape Canaveral, it had already flown past Jupiter, Saturn, and Uranus before reaching the final planet on its grand tour. When it arrived at Neptune, it had only 36 hours of close observation before its trajectory carried it past and onward into interstellar space. 36 hours. That is all humanity has ever gotten. In those 36 hours, Voyager 2's cameras and instruments transmitted back data that scientists are still analysing decades later. The Great Dark Spot appeared in stunning detail. The winds were clocked. The magnetic field was measured and found to be tilted in ways nobody predicted. 6 new moons were discovered in real time as the images came back. The ring system, previously only hinted at by Earth-based observations, was photographed clearly for the first time. And one discovery above all others stunned the science teams watching the data arrive at the Jet Propulsion Laboratory in California. Neptune's largest moon, Triton, showed geysers, active eruptions on a moon so cold that its surface sits at -391 degrees Fahrenheit, the coldest surface measured in the solar system. Geysers of dark material shooting 5 miles into the nearly non-existent atmosphere before being carried downwind into dark streaks across the frozen surface. Scientists had expected Triton to be a geologically dead, frozen ball. Instead, Voyager 2 found a world with active geology driven by a mechanism nobody had anticipated. The thin atmosphere of nitrogen over Triton absorbs enough radiation to heat the subsurface slightly. When that warmth builds up beneath the solid nitrogen ice on the surface, the ice vaporizes and erupts upward through cracks. A geyser powered not by underground heat, but by a star's radiation from over 2.5 billion miles away. For the science teams, the 36 hours of data were overwhelming. Each new image revealed something unexpected. The planet below was more complex, more active, and more strange than any model had predicted. And then the window closed. Voyager 2 continued outward. Neptune shrank in the cameras. The 36 hours ended. Since then, every observation of Neptune has come from Earth-based telescopes, or space telescopes like Hubble. The resolution is a fraction of what Voyager 2 achieved at close range. Scientists watching Neptune's storms change from Earth are working from blurry images compared to the sharp detail Voyager 2 captured in those few hours. Everything known about Neptune in close detail comes from 36 hours of observation in 1989. A crew spending even a single year in Neptune's orbit would return with more knowledge than humanity has accumulated about the planet in its entire history of observation. But getting a crew there and keeping them alive long enough to do that science requires solving problems that push into territory beyond chemistry and biology, into energy scales that make conventional rockets look like bottle rockets. Every limitation covered so far, the fuel problem, the radiation exposure, the 15-year body breakdown, all of them connect back to one root issue. Speed. The faster a ship can reach Neptune, the less time the crew spends absorbing radiation, the less time their bodies spend deteriorating in zero gravity, and the smaller the life support supply the ship needs to carry. Cut the transit time from 15 years to 2 years, and most of the biological problems become manageable. Cut it to 6 months, and a round trip becomes genuinely feasible with life support technology that already exists. The engine that could achieve those speeds exists in blueprints, in research papers, and in small-scale experiments. It has never been built at mission scale. It involves controlled nuclear reactions, and it produces levels of thrust that make chemical rockets look primitive. Nuclear thermal propulsion works by using a nuclear reactor to heat a propellant, usually liquid hydrogen, to temperatures far beyond what chemical combustion can reach. The superheated hydrogen expands and exits through a nozzle at much higher velocity than the exhaust from a chemical rocket. Higher exhaust velocity means more thrust for the same amount of propellant. The rocket equation becomes dramatically more favourable. A nuclear thermal engine could potentially cut the transit time to Neptune to somewhere between 3 and 5 years, depending on the design. The United States developed nuclear thermal rocket engines in a program called Nuclear Engine for Rocket Vehicle Application in the 1960s and 70s. The engines were ground-tested and performed as designed. They were never flown because the political climate around nuclear technology in space shifted, funding was cut, and the specific missions that would have required them were cancelled. The concept sat dormant for decades. In recent years, both government space agencies and private research organisations have revived interest in nuclear thermal propulsion for exactly the reason the Neptune problem illustrates. Chemical rockets cannot practically reach the outer solar system with a crew. Nuclear thermal engines potentially can. Even more powerful on paper is nuclear pulse propulsion, a concept from the late 1950s that involved detonating small nuclear devices behind the spacecraft and riding the shockwave. Calculations suggested it could achieve speeds that would reduce a Neptune transit to months rather than years. The concept was never built. The political and safety barriers to testing a spacecraft that works by setting off nuclear explosions remain absolute. Fusion propulsion sits even further out. If a compact fusion reactor could be built and harnessed for thrust, the specific energy available would dwarf anything else on the drawing board. Transit times to Neptune, measured in weeks rather than years, become theoretically possible. Fusion propulsion research has advanced in recent years, but remains far from producing a working engine at any scale. Each of these technologies removes one layer of impossibility from the Neptune mission. A faster ship means less radiation. Less radiation means lighter shielding. Lighter shielding means more of the mass budget goes to fuel and supplies. Faster transit means less food. Less food means less mass. The cascade that traps conventional missions starts to run in reverse. But every one of these engines still requires getting a crew to Neptune and then getting them back. And there is one option engineers quietly discuss that removes the return trip entirely. There is a version of the Neptune mission that solves almost every problem discussed so far. It solves the fuel problem completely. It solves the return trip mass cascade. It simplifies the life support requirements dramatically. It removes the pressure of a return launch window. It eliminates the fuel needed to decelerate back into Earth orbit. The crew does not come back. A permanent outpost at Neptune, staffed by volunteers who travel knowing they will spend the rest of their lives there, has been discussed in serious scientific and philosophical circles for years. The mathematics of a one-way mission are genuinely more favourable. Carrying return fuel is the single largest driver of mission mass. Remove that requirement and the design space opens up considerably. One-way human missions have a precedent, of sorts. The earliest European settlers who crossed the Atlantic in wooden ships had no guarantee of return. Some signed contracts binding them to years of labour before any possibility of going back. Many never returned. The mission of spreading humanity to a new world was considered worth the individual sacrifice. Proponents of a one-way Neptune outpost make a similar argument scaled to the solar system. If humanity is ever to become a multi-world species, someone has to be first to a place where survival requires permanent commitment. Neptune's moon Triton, with its active geology and confirmed nitrogen atmosphere, has been suggested as a candidate for an outpost site. The problems with this concept are severe and worth stating clearly. Triton's surface temperature is -391 degrees Fahrenheit. The nitrogen atmosphere is 100,000 times thinner than Earth's atmosphere, providing essentially no protection from radiation or meteorite impact. Any outpost would need to be completely enclosed, completely pressurized, completely self-sustaining, and continuously heated against a cold that no habitat on Earth has ever had to withstand. The engineering requirements for even a minimal permanent outpost on Triton exceed anything humanity has built for space habitation. Supplying such an outpost periodically from Earth would require transit times of 15 years per delivery with current technology. By the time a supply ship arrived, the situation it was responding to would be 15 years old. The outpost would need to be genuinely self-sufficient in food, water, air, and basic manufacturing from the moment the crew arrived. No technology currently exists to make that self-sufficiency possible. And the ethical dimension is significant. Asking volunteers to commit to permanent exile at the edge of the solar system is different from asking them to accept mission risks. It is asking them to give up Earth, family, culture, and any changing future forever. Whether any institution should fund or organise such a mission is a question that goes well beyond engineering. But the question keeps coming back, because Neptune is not going anywhere. The mission gets harder to ignore as the outer solar system starts revealing what it contains. Every planet discovered before Neptune was found by looking. Ancient astronomers watched the sky over years, noticed that certain bright points moved against the fixed stars, and identified them as planets. Uranus was spotted through a telescope in 1781 by an astronomer scanning the sky. Every discovery before Neptune was observational. Someone saw something. Neptune was found by calculating where it had to be. By the 1840s, astronomers tracking the orbit of Uranus had accumulated a problem. Uranus was moving in ways that did not match the gravitational influence of the planets already known. Its orbit contained small irregularities, tiny deviations from where mathematics predicted it should be. These deviations were not random. They followed a pattern suggesting a gravitational pull from an unknown source. Two mathematicians working independently reached the same conclusion at roughly the same time. John Couch Adams in England and Urbain Le Verrier in France both worked through the math and produced predictions for where an unknown planet must be located to explain Uranus's irregular orbit. Le Verrier's calculations were passed to the Berlin Observatory in September 1846. The astronomer Johann Galler pointed a telescope at Le Verrier's predicted coordinates that same night. Neptune was exactly where the math said it would be, within 1 degree of the predicted location. This was, at the time, one of the most dramatic confirmations of mathematical physics ever achieved. The idea that you could discover a world you had never seen by calculating where it must exist, based purely on the gravitational influence it exerted on another planet, was startling. It demonstrated that the laws of physics were not just descriptions of what was already known, but tools capable of revealing the unknown. Neptune's discovery represented a kind of confidence in science that spread well beyond astronomy. If mathematics could find an invisible planet at the edge of the solar system, perhaps mathematics could find anything. For a crew travelling to Neptune, this history adds a layer to the mission's meaning. The planet was known through its effects before it was ever seen directly. Scientists understood aspects of Neptune's mass and orbit before a single photograph existed. 200 years of mathematical analysis and telescope observation have built a picture of Neptune that is far more detailed than the planet's one visit from a spacecraft might suggest. And that mathematical understanding revealed something unexpected about where Neptune sits in the solar system's history. Something that changed how scientists think about how the entire solar system formed. Among all the moons orbiting all the planets in the solar system, Triton stands in a category almost entirely alone. Every large moon orbiting a planet in our solar system orbits in the same direction the planet rotates. This is because moons form from the same spinning disk of material that forms the planet. They inherit the rotation. The same way water draining in a sink spins in a consistent direction, moons formed alongside their planet orbit in a predictable direction. Triton orbits Neptune backwards. A retrograde orbit means Triton circles Neptune in the opposite direction to Neptune's rotation. This is physically impossible for a moon that formed alongside Neptune. A moon with a retrograde orbit could only get there one way. It came from somewhere else and was captured by Neptune's gravity after Neptune had already formed. Triton is a captured object from the outer solar system. Scientists believe it originated in the Kuiper Belt, a vast region of icy objects beyond Neptune's orbit. At some point in the early solar system, Triton wandered into Neptune's gravitational reach. What happened next is the violent part. Capturing a large object into a stable orbit does not happen gently. A capture event requires energy to be transferred. The most likely mechanism scientists have identified involves Triton originally being part of a binary system, two objects orbiting each other. When this pair encountered Neptune, gravitational forces split the binary apart. One object was flung away into deep space. The other was captured into orbit around Neptune. The energy from breaking the binary provided the braking needed to trap Triton in orbit. This event would have been catastrophic for whatever moons Neptune had already formed. The arrival of a large captured object on a retrograde orbit would have gravitationally disrupted the existing moon system. Scientists believe the original moons of Neptune were either ejected from the system or collided with each other during this violent rearrangement. Triton's retrograde orbit carries another consequence. Because it orbits backwards against Neptune's rotation, tidal forces between the planet and the moon are slowly draining energy from Triton's orbit. With each orbit, Triton moves fractionally closer to Neptune. The process is imperceptibly slow on human timescales. But it is relentless. In roughly 3.5 billion years, Triton will cross what scientists call the Roche limit, the distance at which Neptune's tidal forces overcome the gravity holding Triton together. At that point, Neptune will pull Triton apart. The moon will shatter into billions of pieces, spreading into a ring system around the planet far larger and more dramatic than anything Neptune currently shows. Neptune will gain a ring system that rivals Saturn's. 3.5 billion years from now. For a crew studying Triton from orbit, this slow death is written into the moon's very motion. Every measurement of Triton's orbital decay is a countdown timer running across geological time. The most extraordinary natural disaster in the solar system is already scheduled. The crew would just be measuring how far along the countdown has gotten. And what else Triton's captured origin tells scientists about Neptune's history reaches further than anyone expected. Triton's arrival into Neptune's orbit was not just a local event. It was part of a solar system-wide reorganization that scientists now believe shaped every planet's position, including Earth's. The Grand-Tack hypothesis and the NICE model are two frameworks astronomers have developed to describe how the outer solar system's giant planets moved dramatically in the early history of the solar system. Both involve Neptune playing a central role in a period of gravitational chaos that lasted hundreds of millions of years. Early in the solar system's history, the giant planets including Jupiter, Saturn, Uranus and Neptune all orbited closer to the star than they do now. As they grew in mass, they began gravitationally interacting with the enormous disk of icy debris in the outer solar system. This interaction transferred momentum. The planets began migrating outward. Neptune, which models suggest may have originally orbited closer to Uranus, drifted outward to its current position over tens of millions of years. As Neptune moved outward, it swept through the outer debris disk like a plough. Objects in its path were either captured into resonant orbits, flung into the inner solar system, or ejected entirely into the space beyond the planets. Scientists believe this outward migration of Neptune was responsible for a period called the Late Heavy Bombardment, roughly 3.9 billion years ago, when the inner solar system, including Earth, was struck by a dramatically increased number of large impacts. Every crater on the Moon from that era carries Neptune's fingerprint. The water on Earth, essential for life, is believed to have been delivered partly by icy objects from the outer solar system during this bombardment period. Objects whose orbits were disrupted by Neptune's migration. Neptune's movement billions of years ago may be directly responsible for Earth having oceans. And oceans made life possible. A crew at Neptune would be orbiting the planet that, in the most indirect but scientifically supported chain of events, helped create the conditions for their own existence. The distant planet that shaped the inner solar system's water budget. The gravitational sculptor that sent ice to Earth. This history is known not from direct observation, but from the mathematical fingerprints Neptune left on every other object in the solar system. The distribution of objects in the Kuiper belt, the orbital resonances of smaller bodies far beyond Neptune, the cratering record on the Moon, all of these trace back to Neptune's early migration. A crew doing science in Neptune's orbit would be studying the source of much of what made Earth livable, and they would be doing it in conditions that make Earth's worst environments seem gentle. The cold, the darkness, the radiation, the isolation, these are the price of standing at the place where so much of Earth's history began. And yet, despite how much Neptune has shaped our solar system, and despite everything known about it from calculations and distant observation, almost nothing about it has been seen up close. The view approaching Neptune from space is something no human eye has ever experienced. And it is extraordinary. Approaching Neptune from space, the first thing that registers is the colour. Every planet has a visual signature. Mars is a dusty red-orange from iron oxide across its surface. Jupiter is banded in cream and brown, and orange from complex atmospheric chemistry. Saturn glows pale gold, its rings extending in geometric precision. Uranus appears a soft, muted blue-green. Neptune is a different category entirely. The blue of Neptune is not the pale blue of a clear sky or the medium blue of a shallow ocean. It is deep, saturated, rich in a way that does not look natural compared to anything else in the solar system. Scientists describe it as cobalt or royal blue, but even those comparisons fall short when looking at Voyager 2's actual photographs. The colour appears almost electric against the black of space. Methane in Neptune's atmosphere creates this colour through selective absorption. Methane molecules absorb red and infrared wavelengths of light and reflect blue wavelengths back. Uranus has a similar methane concentration, which is why it also appears bluish. But Neptune's blue is noticeably more intense, and scientists have not yet fully explained why. Something else is in Neptune's atmosphere that enhances the colour beyond what methane alone can produce. The leading theory involves an unknown chemical compound, possibly a product of photochemical reactions, high in the atmosphere where radiation breaks apart methane and other molecules, creating new compounds that have not been identified from Earth-based observation. A crewed mission in orbit could collect atmospheric samples and potentially solve this 40-year mystery within weeks. Approaching from thousands of miles away, the planet would fill the view gradually. The disk would grow from a bright blue dot to a sphere, the blue deepening in the centre, where the atmosphere is thickest, and paling slightly at the edges where you are looking through a thinner slice of atmosphere. Bright white streaks of methane ice cloud would be visible moving across the surface at the 1,200 mile/hour wind speeds the crew had spent years dreading from a safe distance. The ring system would become visible as the ship drew closer. Neptune's rings are dark and faint compared to Saturn's brilliant ice rings. They consist of dust and small rocky particles, likely debris from moons that were disrupted by Triton's violent capture event billions of years ago. The rings are clumped unevenly, with denser arcs of material interspersed with gaps, a structure that puzzled scientists when Voyager 2 first imaged them and remains only partially explained. Triton would be visible from orbit as a pinkish-white sphere, its surface coloured by nitrogen frost and complex organic compounds called tholins that form when radiation strikes nitrogen and methane in the thin atmosphere. The geysers Voyager 2 detected would be invisible at orbital distance, but instruments would confirm they are still active. No human has seen any of this directly. Every image of Neptune in human history was captured by a camera, either on a spacecraft flying past at high speed or on a telescope hundreds of millions of miles away. The actual visual experience of approaching this blue world, of watching it grow from a point to a globe to something that fills the windows, belongs to a future crew that has not yet left the ground. Getting that crew to Neptune and keeping them alive for the return journey depends on solving problems that are still open. But the way scientists approach those problems has shifted in one unexpected direction. The crew has been travelling for 8 years. Physically, they are deteriorating. Psychologically, they are stressed. They have consumed roughly half their food supply and watched dozens of systems degrade toward their maintenance thresholds. They are still 7 years from Neptune. A doctor reviewing their health data would be concerned. An engineer reviewing the ship's systems would be concerned. A psychologist reviewing the crew's behavioural logs would be very concerned. Now imagine instead that the crew boarded the ship, entered a temperature-controlled sleep chamber, and woke up at Neptune. Hibernation, or more precisely induced metabolic suppression, has been a serious topic in space medicine for decades. The concept involves slowing a person's metabolism dramatically, reducing body temperature, slowing heart rate and breathing, and putting the brain into a state that prevents the psychological damage of isolation and boredom, while also reducing the body's need for food, water, and oxygen. Natural hibernation exists across dozens of animal species. Bears, ground squirrels, bats, and many others slow their metabolism during winter months, living off stored fat reserves and emerging weeks or months later with minimal physical damage. Some species of squirrel can lower their body temperature to just above freezing and reduce their heart rate from hundreds of beats per minute to fewer than 10. Humans do not naturally hibernate. The biology of human thermoregulation is different from that of animals that evolved with hibernation as a survival strategy. Cooling the human body causes the heart to develop dangerous rhythms. The brain, highly sensitive to temperature change, does not tolerate cooling the way a squirrel's brain does. Medical researchers studying trauma have found that therapeutic hypothermia, carefully cooling the body to around 89 degrees Fahrenheit after cardiac arrest or traumatic brain injury, can reduce cellular damage during recovery. This is a much smaller temperature change than deep hibernation requires and is maintained only for hours. Extending this to weeks, months, or years would require understanding mechanisms of cellular protection that medicine has not yet mapped. Research projects specifically aimed at long-duration spaceflight hibernation have been funded by space agencies and explored in laboratory settings. Scientists have identified several compounds that trigger hibernation, like states in animals that do not normally hibernate. Injecting hydrogen sulfide in small doses caused mice to enter a state resembling hibernation with dramatically reduced metabolism, then recover normally when the compound was removed. The same approach in larger mammals, including primates, has been less consistent. For a Neptune mission, even imperfect hibernation would represent a massive improvement. If metabolism could be reduced by 50%, food requirements drop by half. If the crew sleeps through most of the transit, the psychological toll of isolation falls dramatically. Bone loss and muscle atrophy during hibernation in animals is notably lower than during normal immobility, suggesting the metabolic state itself may provide some protection. The unknowns are serious. The effects of cosmic radiation on a hibernating brain are completely uncharted. Whether cells in a low metabolism state repair radiation damage more slowly or more quickly is unknown. Whether 15 years of even partial hibernation causes irreversible neurological changes has never been tested in any species. But the direction of the research is the most interesting detail. Every year the science of metabolic suppression advances. The distance to Neptune has not changed. The gap between them is slowly closing from one side. Every planet with a magnetic field generates it through roughly the same process. Liquid, electrically conductive material deep inside the planet moves under the influence of heat and rotation. The moving conductor generates electrical currents. Those currents produce a magnetic field. On Earth, this process happens in the liquid iron outer core, and it produces a magnetic field whose poles sit close to the geographic poles. The field emerges from near the South Pole, arcs through space, and returns near the North Pole. Neptune's magnetic field behaves as if someone designed it to break every expectation. First, the tilt. Earth's magnetic axis is offset from its rotational axis by about 11 degrees, a small angle, small enough that a compass pointing to magnetic north gets you close enough to true north to navigate. Neptune's magnetic axis is offset from its rotational axis by 47 degrees, nearly half a right angle. The north magnetic pole of Neptune sits far from the geographic North Pole, not near it. Second, the off-center origin. On Earth, the magnetic field appears to originate from roughly the center of the planet. On Neptune, the magnetic field's source point is offset significantly from the planet's center, displaced toward one side. This means the field's strength and structure vary dramatically across the planet's surface in ways that simply do not happen on Earth. Third, the complexity. Earth's magnetic field is relatively simple, a dipole, like a giant bar magnet. Neptune's field contains higher-order components, quadrupole and octupole terms in the mathematical description, that give it a complex, lumpy structure, unlike Earth's smooth field. Scientists believe all of this results from where Neptune's magnetic field is generated. On Earth, the source is the liquid iron core, deep in the center. On Neptune, the conducting layer is believed to be the superionic water mantle sitting well above the core, not in the center. A magnetic field generated off-center in the planet naturally produces an off-center, tilted, complex field. This distinction matters scientifically beyond Neptune itself. Uranus has a similarly tilted, off-center magnetic field. Both ice giants appear to generate their fields in a fundamentally different way than the gas giants Jupiter and Saturn, whose fields are more Earth-like in structure, despite the enormous difference in planet type. Understanding how ice giants generate magnetic fields would fill a significant gap in planetary science. Magnetic fields shape whether a planet can hold an atmosphere, whether radiation reaches the surface, and whether conditions for life are possible. A crew orbiting Neptune could map the magnetic field in detail that no telescope or flyby can achieve, flying through different parts of the field at different altitudes, deploying magnetometer probes, and correlating magnetic measurements with atmospheric observations would produce a dataset that scientists on Earth could work with for decades. The magnetic field is also what makes the radiation environment around Neptune complex and dangerous. Where the field is strong, particles are deflected. Where it weakens or gaps, radiation penetrates. A crew navigating Neptune's orbit would need continuous magnetic field data to find the safest orbital paths. Understanding the field is survival planning and science simultaneously, and the science at Neptune keeps connecting back to the strangest moon in the solar system, one that should be frozen silent but turned out to be geologically alive. Triton should be dead. Everything about its environment suggests a frozen, geologically inert world. It sits at minus 391 degrees Fahrenheit, the coldest surface temperature measured anywhere in the solar system. Its tenuous nitrogen atmosphere provides essentially no insulation. It receives almost no heat from its distant star. By every conventional expectation, Triton should be a featureless frozen sphere. Instead, Voyager 2 found geysers, dark material erupting upward 5 miles into the thin nitrogen atmosphere, then carried sideways by upper-level winds, leaving streaks of dark dust across Triton's pink-white frozen surface. Active geological features on one of the coldest objects ever studied. The heat source is unlike anything else in planetary science. Triton's geysers are powered by the planet's own radiation, not internal heat. Triton's surface is covered in transparent nitrogen ice. The distant star's radiation, faint as it is at this distance, passes through that transparent ice and heats the darker material beneath it. It works like a greenhouse effect in miniature. The nitrogen just below the surface absorbs the heat and sublimates, turning from solid to gas, building pressure until it erupts upward through weak points in the surface ice. The energy driving those eruptions comes from a star 2,800,000,000 miles away. Triton is powered by sunlight so faint that it looks like starlight. Beyond the geysers, Triton's surface shows evidence of geological activity far more complex than a simple frozen ball. Large smooth plains suggest ancient cryovolcanism, where liquid water or ammonia once erupted from the interior and refroze across the surface. Ridges and depressions indicate tectonic-style stresses in the ice crust. Scientists believe that when Triton was first captured by Neptune, the tidal heating from its gradually stabilizing orbit warmed the interior enough to sustain liquid water for hundreds of millions of years. Liquid water. In the outer solar system. For hundreds of millions of years, this is why Triton appears on early lists of potentially interesting locations in the search for understanding where life might develop beyond Earth. Not because life exists there now, but because the conditions that scientists associate with prebiotic chemistry, liquid water, organic compounds, energy gradients were present on Triton for a geologically significant period. The tholins colouring Triton's surface are organic compounds formed when radiation strikes nitrogen and methane. These same compounds are found in laboratory simulations of early Earth's atmosphere and in comets that may have seeded Earth with organic material. Triton's surface is covered in chemistry that sits at the boundary between geology and the earliest stages of organic complexity. A crew landing on Triton, if the engineering could be solved, would be stepping onto a surface that has been continuously bombarded by radiation-driven chemistry for billions of years. The scientific value of even a short surface operation would be enormous. The engineering challenges of landing and surviving on Triton are severe but significantly less extreme than anything involving Neptune's atmosphere directly. Triton has a solid surface. Gravity is very low, about 8% of Earth's. The cold is the dominant hazard, and cold, unlike 1,200-mile-per-hour winds or crushing atmospheric pressure, is at least an engineering problem with known solutions. Triton may be the real scientific target. And what orbits beyond Triton tells a story about what Neptune is really the gateway to. Neptune does not orbit in empty space. Beyond it lies a vast region of icy objects called the Kuiper Belt, stretching from Neptune's orbit outward to about 50 times Earth's distance from the star. The Kuiper Belt contains hundreds of thousands of objects ranging from small chunks of rock and ice to dwarf planets large enough to have their own moons. Pluto, the most famous object in the Kuiper Belt, is simply one of the largest members of this population. When scientists reclassified Pluto as a dwarf planet in 2006, the decision was not a demotion, but an acknowledgement that Pluto belongs to a class of objects far more numerous and scientifically interesting than a single planet. Neptune sits at the inner edge of the Kuiper Belt and acts as its gravitational shepherd. Neptune's orbital resonances, the gravitational rhythms created by a large planet's regular passage, sort Kuiper Belt objects into patterns. Some objects are locked in orbital ratios with Neptune, completing 2 orbits for every 3 Neptune completes, or 3 for every 5. Pluto is in this category. These resonant orbits are stable over billions of years because Neptune's gravity keeps reinforcing them. Objects outside these resonances are slowly scattered. Neptune's gravity deflects their orbits over millions of years, sending some inward toward the inner solar system, where they become comets visible from Earth, and others outward into the far reaches of interstellar space. Many of the short-period comets that have been observed from Earth throughout history originated as Kuiper Belt objects scattered inward by Neptune's gravitational influence. Neptune, from the Kuiper Belt's perspective, is not the last planet. It is the gatekeeper, the gravitational filter that determines which objects stay in the outer solar system and which ones get flung elsewhere. For a crew at Neptune, the scientific opportunity extends well beyond the planet itself. From Neptune's orbit, a spacecraft could efficiently reach multiple Kuiper Belt objects during a single mission. The delta V, the velocity change required to move between objects, is manageable from Neptune's orbit in ways that would be far more expensive from Earth. A mission to Neptune could simultaneously be a mission to the Kuiper Belt, studying the primordial material left over from the solar system's formation billions of years before the planets existed. This material is scientifically priceless. The Kuiper Belt objects are the solar system's most pristine preserved samples, unchanged since the earliest period of planetary formation. Understanding their composition would reveal details about the conditions that existed when Earth formed, what materials were available, what chemistry was possible, what the young solar system actually looked like. Standing at Neptune, a crew would be at the edge of the familiar solar system. Beyond Neptune's orbit, the solar system transitions from planets to something older and less organised, the boundary between the structured planetary zone and the primordial debris field beyond. The edge of everything charted, the beginning of everything else. And looking back from that edge reveals something about our home that no other vantage point can offer. On February 14th, 1990, the Voyager 1 spacecraft was 4 billion miles from Earth when scientists instructed it to turn its camera around and photograph the solar system it was leaving behind. The resulting image showed Earth as a fraction of a single pixel, a pale blue point suspended in a beam of scattered sunlight. Astronomer Carl Sagan called it the pale blue dot. He wrote that every human who had ever lived, every king and farmer and soldier, every civilization in all of history, had spent their entire existence on that tiny point. A crew at Neptune would see something even more extreme. From Neptune's distance, Earth is completely invisible to the naked eye. The planet is too small and reflects too little light to be distinguished against the background of stars. The star itself is visible, an intensely bright point, the dominant light source in the Neptune sky, but shrunk down to a point of light rather than a blazing disk. The entire inner solar system, Mercury, Venus, Earth, Mars, and the asteroid belt, would be compressed into a region of sky smaller than your thumbnail held at arm's length. Jupiter and Saturn would be visible with the naked eye as bright points. Uranus would require binoculars, Earth would require a telescope. This view would do something to a crew that no psychology experiment on Earth can replicate. The cognitive and emotional experience of watching your home planet vanish entirely, not shrink to a dot the way astronauts on the space station describe, but actually disappear from unaided view, is something that no human has yet processed in real time. Space psychologists studying this theoretically predict that the experience would be deeply destabilizing for some crew members and oddly liberating for others. The loss of Earth as a visible anchor changes the psychological relationship to the mission. The crew is no longer travelling away from something visible. They are in a place where home exists only as a known direction in empty space. Instruments and navigation computers would tell the crew exactly where Earth is. They could point a telescope and find it with precision. But pointing a telescope toward home and seeing a faint point of light among millions of other points of light is not the same as looking out a window and seeing a blue sphere. The scientific value of this perspective is distinct from the emotional weight. From Neptune's position, instruments looking back into the inner solar system can observe things that are impossible to observe from inside that region. The distribution of dust in the asteroid belt, the orbital dynamics of the inner planets, the structure of the solar magnetic field in the inner system, all of these are easier to study from a distant vantage point where the geometry works in the observer's favour. A crew at Neptune would be doing science that can only be done from there, observing home from the only angle that reveals things invisible from home itself. The distance that makes the mission so dangerous is the same distance that makes the mission scientifically irreplaceable. And yet, despite everything, every calculation, every biological limit, every engineering constraint, the conversation about sending humans to Neptune keeps returning. Because the alternative, leaving the outermost planet permanently unvisited by humans, carries its own cost. The Neptune mission has been declared impossible more times than almost any other proposed human spaceflight. The fuel problem closes the door on it. The biology problem closes the door on it. The radiation problem closes the door on it. The psychology problem closes the door on it. The supply problem closes the door on it. And yet the mission keeps reappearing in research discussions, funded concept studies, and serious planning documents. The reason is simple. Every major advance in propulsion, life support, and space medicine moves the math slightly further toward possible. Ion drives, which were considered experimental in the 1990s, now power operational spacecraft routinely. Solar sails, once purely theoretical, have been tested in space. Nuclear thermal propulsion research has been restarted with government funding after decades of dormancy. Closed-loop life support systems, which recycle air, water and waste with increasing efficiency, are being developed for the planned Moon and Mars missions and will be directly applicable to Neptune. The biological understanding of long-duration spaceflight is accumulating with every crew member who spends a year on the space station. Each data point adds to the model of what happens to a human body in deep space, and what countermeasures help most. The mission to Neptune that seemed purely abstract 50 years ago now has a biological dataset to design against. Artificial intelligence capable of real-time onboard decision-making without ground support is developing rapidly. A crew at Neptune, cut off from Earth's response time, needs systems that can diagnose ship failures, calculate solutions, and implement repairs with minimal human input during the critical moments when the 8-hour communication gap makes ground support irrelevant. Onboard artificial intelligence systems that could handle this level of autonomous problem-solving are closer than they have ever been. 3-dimensional printing technology being developed for space applications could address the long-tail spare parts problem. If a crew can manufacture replacement components from raw material stocks rather than carrying pre-built spares for every conceivable failure, the mass required for redundancy drops significantly. Early space-based manufacturing experiments have already demonstrated the concept at small scale. Each of these developments does not solve the Neptune problem alone. Together, they reduce the unsolvable parts of the equation one piece at a time. Engineers who work on outer solar system mission planning say the same thing consistently. Neptune is a question of when, not whether, given enough development across enough technologies simultaneously. The planet is not going anywhere. The scientific value of a crewed mission grows with each new discovery about the outer solar system. The technology to make the mission survivable is advancing from multiple directions at once. The mission that is impossible today was also impossible in 1960 for the Moon. The tools change. The math changes. The mission eventually moves from impossible to difficult to achievable. The question that remains is what exactly a crew would learn at Neptune that makes the difficulty worth it. Scientific probes have visited every planet in the solar system. Robotic landers have touched the surfaces of the Moon, Venus, Mars, and Titan. Orbiters have mapped Jupiter, Saturn, Uranus, and Neptune from varying distances. Rovers have driven across Mars for years. The history of planetary exploration is, at this point, largely a history of what robots have accomplished on humanity's behalf. So the question that gets asked every time a crewed Neptune mission comes up is a fair one. Why send humans at all? Why accept every biological, psychological, and engineering impossibility described in the previous chapters when a better robot could do the science more cheaply and more safely? The answer involves several things that robotic exploration consistently struggles with, even as robotics improves rapidly. Adaptability in real time. A robotic probe operates on pre-programmed instructions or on commands sent from Earth with a communication delay. At Neptune, where commands take over 4 hours to arrive and responses take over 4 hours to return, A probe encountering an unexpected situation must either wait 8 hours for guidance or operate within the limits of its autonomous programming. A human scientist on site can recognize an unexpected discovery, redesign the investigation on the spot, redirect instruments, and pursue the anomaly within minutes. Some of the most important scientific discoveries in history came from investigators following an unexpected observation that no protocol had anticipated. Sample handling complexity. Collecting, cataloguing, and analysing physical samples from Triton or from Neptune's atmosphere requires a degree of judgment, manual dexterity, and adaptive decision-making that robotic systems have not achieved at the level planetary scientists need. Mars sample return missions involve enormous engineering complexity just to collect and preserve samples for Earth analysis. At Triton, where the chemistry of the surface involves fragile organic compounds at extreme temperatures, a human scientist with the right tools could accomplish in hours what would take a robotic mission years and multiple generations of hardware. System repair. When something goes wrong with a robotic spacecraft, it is frequently permanent. Voyager 2 lost the use of several instruments over its mission with no recourse. A crewed mission carries engineers who can repair, improvise, and solve problems that no design team anticipated. The history of human spaceflight is full of missions saved by crew members fixing things that were not supposed to break. The scientific intuition that drives discovery is harder to program than the instruments that measure it. A human scientist watching the colour of a geyser plume on Triton change unexpectedly would know immediately that this was interesting and why. A robotic system would need to have been specifically programmed to recognise that change as significant. None of this makes the mission less dangerous. The impossibilities described throughout this journey are real. The body still degrades. The fuel equation still struggles. The radiation still accumulates. The isolation still damages. But the return on the scientific investment of a crewed Neptune mission would be unlike anything robotic exploration can offer. A year in Neptune's orbit with a skilled crew doing adaptive science would produce discoveries that would anchor planetary science for the rest of the century. The mission is worth solving. That is why engineers keep solving it. Neptune exists at a distance that makes it feel like it belongs to a different universe. 2,800,000,000 miles from Earth, unreachable with today's technology for a crew hoping to return. Visited once, briefly, by a probe that is now billions of miles past it and still going. And yet Neptune has shaped Earth more than most people realise. The water in your body arrived on this planet partly because of Neptune. The gravitational migration of Neptune through the early solar system sent icy debris inward, delivering water molecules to a young Earth that was too hot and too close to its star to form water on its own. The oceans came from the outer solar system. Neptune helped send them. The carbon compounds in every living cell on Earth were part of a solar system-wide distribution of organic chemistry that Neptune's gravity influenced. The Kuiper Belt objects scattered inward by Neptune's migration carried complex organic molecules into the inner solar system, contributing to the chemical inventory available when life began forming. Neptune is not a remote stranger. It is part of the causal chain that made human life possible. And what Neptune has yet to teach us is substantial. The magnetic field that does not behave like other magnetic fields. The weather system that generates 1,200 mile/hour winds with almost no energy input from its star. The supersonic water ocean that exists in a state of matter that human science has produced only in laboratories for fractions of seconds. The moon that should be frozen dead but erupts geysers from sunlight alone. The orbit that is counting down to a catastrophic disruption 3.5 billion years in the future. Each of these is an open question. Each has implications that extend beyond Neptune. Understanding how ice giants generate magnetic fields would help scientists model planets around other stars. Understanding Neptune's internal heat source would refine models of how planets store and release energy over billions of years. Understanding Triton's captured origin would sharpen the picture of how the early solar system's chaos resolved into its current structure. The knowledge is sitting at Neptune, waiting, accumulated over 8.5 billion years of planetary evolution, representing conditions and processes that do not exist anywhere closer to Earth. The mission that seems impossible today will look different in 50 years. New engines will exist. Biology will understand space better. Materials will be stronger and lighter. Computers will be more capable. Hibernation research will have produced results. The gap between Earth and Neptune will not have changed by a single mile. But the gap between what humanity can do and what the mission requires will have narrowed. Some crew, in some future that the people alive today will not see, will approach Neptune for the first time with human eyes. They will watch that deep blue sphere fill the windows. They will see the storm systems churning below. They will detect Triton's geysers firing into the thin nitrogen sky. They will be cut off from Earth by 4 hours and 10 minutes of radio travel time, with bodies that have spent years adapting to deep space, in a ship that has survived everything the void has thrown at it. They will not be coming back. Or they will, depending on what that future has solved. Either way, they will know something the rest of humanity does not. What it feels like to stand at the edge of the solar system and look back toward a star that is just another bright point in the dark. And they will understand, at a level no telescope or calculation can replicate, exactly what kind of universe we actually live in.